Test, 1, 2, 3. How about now? Okay, I'm worrying about sound right now, but sound, can we hear? Test, 1, 2, 3. Audible?
Yep.
Good.
And the camera's also.
And the camera. That was the issue. So everybody should have gotten their exam back. And these are the statistics for the exam. It looks like the average was really average. High, low. I've had much worse lows, so you benefit from having TAs this semester who are easy graders. So it doesn't look like I will need to do any curving right now. But that can change after the second exam. Be aware of that. And then I just want to go through the problems on the exam. And again, I'm not going to crunch numbers. I'm just going to set them up for you. And the graduate students slaved 2 weeks, not only doing your exams, but your labs and your homeworks. So they don't want to see your exams for at least another 2 weeks. If you have questions on your exams, bring them to me. Send me an email. We can set up a Zoom. The idea of going through this today is maybe I can clear up a lot of questions. If you have specific questions on your specific exam, we'll set up a call or a Zoom meeting for every problem, whether it's homework, labs, or the exams. We set up a grading rubric before we even grade. We're going to give so many points for each of these components. That is to make sure we're very consistent when we're grading. The last thing you want to do is bring your exam to me and say, I got 2 points taken off here and my friend got 1 point taken off here. Because then I want to see your friend's exam. I may have to take a point off theirs because I have to compare it to the rubric. So moral of the story is you can certainly ask about how points were taken off on your exam. But once you start your comparing to someone else, I want to see that someone else. It's just to be consistent and fair. That's what I'm trying to do. So I'm not just going to give you a point just because someone else maybe got a point they shouldn't have. And I'm more than willing to work through all your exam problems with you if you would like to do that. So in the very, no temperature. In the very first problem, you're asked when you have a liquid poured into a graduated cylinder. So here's our graduated cylinder. You're told what the volume is. And you're given that it weighs a certain amount. And you're asked to calculate the specific weight, the density, and we'll call it rho x, gamma x, and the specific gravity of this material. So you know from your homework problems, and you can certainly compare all of your test problems to all of the homework problems, either collected or not, you will see there are similarities between many of them. So in this case, the specific weight is by definition the weight per unit volume. And so you're given the weight, you're given the volume, so you can calculate the specific weight. Density is specific weight divided by the acceleration due to gravity. And lastly, the specific gravity of anything is equal to either the density of X to the density of water or the specific weight of fluid X compared to the specific weight of water. That one was pretty straightforward. And there you just needed to know the conversion from milliliters to liters. And again, I will post this for you, so you don't really have to feverishly copy unless you'd like to. On the next one, you're given crude oil. It has it with a viscosity, and it's between two parallel plates. So here are two plates, and the lower plate moves. The upper plate moves, the lower plate is stationary. So the upper plate is moving at a velocity of 3 foot per second. The lower plate is not moving, it's fixed. And what we see is that we have this velocity of 3 foot per second. And to create this, we would need to apply some force P to get this plate moving. Otherwise, without P, it's just going to sit there. And again, yeah, you have a fluid in here, it's the oil, and it's got a pressure distribution, but what's counteracting the movement or the force P is the shear stress. So again, pressure is normal to the surface. That's not giving us a force parallel to the surface. And what we're trying to figure out is how do we calculate this force P to get this condition? And once you see that you have the shear stress, so let's do a free body diagram. We've got P acting here, and then the shear force acting on the bottom, which is just the shear stress times the shear area. I did an example like this in class. So in this case, some of the forces, if to the right is positive X, are equal to 0, that would equal to P minus the shear force, which then P is equal to the shear stress times the shear area. And so you can calculate the shear stress from Newton's law of viscosity. So you're given the distance between the plates as 1/10 of an inch. You're given the velocity of the upper plate and the lower plate, so you know the change in velocity through the fluid. And you're given this viscosity, and so you can calculate the shear stress. And then again, if you are given the area of the plate, that's the shear area also, then you can calculate everything on the right-hand side and get the force. Okay. On the next one, again, part of this is recognizing what kind of a problem you have. And in this case, it's saying we're trying to determine the bulk modulus of elasticity. And we were only given one equation for bulk modulus of elasticity. And remember, how it was developed was by looking at the stress-strain relationships of fluids under compression or expansion. And we first defined compressibility, and then the inverse of compressibility is the bulk modulus of elasticity. So by definition, the bulk modulus of elasticity is equal to negative change in pressure divided by the percent change in volume, which is dV over V. So dP is equal to the final pressure minus the initial pressure. dV, the change in volume, similarly is the final volume minus the initial volume. And the volume here is the initial. That's how we get the percent change. You're comparing it to the initial condition. So in this problem, you see that you have the initial and the final pressure. Final is 3,000 PSI, initial is 15 PSI. You have the initial and final volumes. It starts at 10.24 cubic inches and goes to 10.138 cubic inches. So you have not only the difference in volume, but also the initial volume. And so again, obviously, since the volume decreases, that's a negative number, which counteracts the negative in front of the general equation. And so that would give you the bulk modulus of elasticity. On problem 4, I show the figure on the next page. So what we're going to see is that we have this U-tube manometer on the left side of a tank. The tank has air on the top and water on the bottom. And on the lower right-hand side of the tank is a pressure gauge, and that's what we're trying to find. What is the pressure reading on the pressure gauge on the right-hand side? And in this case, you're given that on the manometer on the left-hand side, there's an airspace above the gauge fluid, and you're given a pressure in absolute pressure terms. Absolute pressure measurement data. And you're asked to give the answer in gauge pressure. So you had to assume standard atmospheric pressure somewhere. So again, what's the pressure in the gauge on the right? This is what we're after, the pressure here. Some people were asking, where is that? It doesn't matter. where the difference in those water surfaces are. Why? Because again, we assume that for gases, dPdZ is basically zero, that we don't see a change in pressure as we move through gases in the vertical compared to liquids. Okay, so it doesn't matter where that is. And anything you could have assigned any distance. If you look at this figure, it's obviously less than 4 feet, right? So let's say you assumed 1 foot. No matter what you assumed, you would find by calculating whatever pressure difference in air there is between these locations is like at the 4th decimal place. It's negligible. So to solve this, again, this is a manometer problem. And what we're going to do is start over at this location. So let's call this point 1. And we're going to work through the system in a piecewise continuum fashion and go over to the gauge here, which we'll call P2. That's the gauge pressure. So we start at P1. And again, at P1, you're given a pressure, an absolute pressure datum. So we're going to work the whole problem in absolute pressure. We'll calculate P2 in absolute pressure. And then all we have to do, as you see in another problem on the same exam, subtract off atmospheric pressure to get gauge pressure. So starting there, I know the pressure, and we're moving down to this location. Let's call that A. We're moving in the vertical, and we're going in the negative Z direction or the positive H direction, which is an increasing pressure direction. So from P1, we would increase the pressure, the distance, 4 feet, times the specific weight of the fluid, and I'm just going to call that gamma X. So that would be the pressure at A. We don't really want the pressure at A, but now you have it. And why we use that point is we know that dP dx is 0, so we can go horizontally over from A to the other side of the manometer because you have a continuum. You can only use dP dx is equal to 0 if you have a continuum. There's no change in pressure when we move horizontally. And again, that pressure here is the same pressure here because we're just moving through air. We don't need to know that difference in elevation. And so now all we have to do is get down to the elevation of the gauge. And so again, we're going to start at this fluid surface where we actually still have PA, pressure A. And we're going in the vertical direction downwards. That's an increase in pressure, plus 2 feet is the distance we go through, times the specific weight of water. And that's P2. And then again, this is in absolute pressure. And therefore in gauge, all we have to do is take an absolute pressure and subtract off atmospheric pressure. Local atmospheric pressure, it is actually in the back of your book and it's given in various problems, but typically around here it's 14.7 psi A. If you guess something close to that, that's fine. Again, it's in the back of your book under the air pressure tables or fluid properties for air and standard atmospheric pressure, and they tell you in the back of the book appendix what atmospheric pressure is at sea level, which is almost what we're at. So that's how we would solve problem 4. And problem 5 was probably the hardest problem on the exam. And again, if you could set it up, you get 80% of the points. But the figures on the next page, you have this gate that is 4 feet by 8 feet. And it's inclined on an angle of 60 degrees off of the horizontal, as you'll see. And there's the gate itself weighs 800 pounds. And it's held in place by the horizontal cable, as you will see in the figure. Water is on one side of the gate. And so we want to know if it's hinged at the bottom, what's the tension in the cable necessary to support the system in equilibrium. So here's the system. And the first thing we're going to do is draw a free body diagram. So here's the gate. And now we're going to analyze or assess all the forces on it. You know you have a weight. We know we're going to have a force of the water on the gate. And we've got this cable. And we have a pin connection at A. And so as I've stressed to you, you have these reaction forces in the vertical and maybe the horizontal direction. And I'm just assuming those directions. So if you do a force balance, either in the X or the Z direction, you need to know those reaction forces. And you won't be able to solve those equations because you don't have enough equations. You have too many unknowns. What are the unknowns? The tension in the cable and FAX and FAZ. So what you could do is look at some of the moments about A. And we know that those have to equal to 0 because this system is static. And if that's true, then what we need to know is the moment arms for each one of these forces. So for example, that moment arm is L1. It's the moment arm for the water force. The moment arm for the weight is L2. Where does the weight act? At the center of the gate. The moment arm for this is going to be at distance, L3. Okay, and so we can take this equation and we can say that clockwise positive FW L1 is a moment of the water force about A, clockwise direction. The weight, clockwise direction, times L2. And then the tension force is counterclockwise direction. If it was moving, it would be pulling this gate in a counterclockwise rotation, and that would be times L3. So we're after T, the tension in the cable. That means we need to find everything else. L3 is from the geometry. We know the gate is 8 feet in height. Only 6 feet of it is submerged. That affects the force of the water. But if the gate is 8 feet in height, then L3 is equal to 8 foot sine of 60. Remember, y sine of theta is equal to any vertical measurement h in all these problems. So we know L3, we're trying to get T. L2 is, again, if the weight is acting half of the distance down along the gate, and we're trying to calculate, again, L2. Then L2 is going to be a function of this geometry. L2 in this case is the 4 foot cosine of 60. So again, if this is 60 degrees, this is 60 degrees. And we're trying to find L2, which is cosine of 60 degrees times 4 feet, the distance along the hypotenuse from where the weight acts down to point A. And then L1 is going to be a function of the distance to the center of pressure. So I'm going to get to that. So again, we can knock these all out. Weight was given, 800 pounds. And so now we need to know the force of the water in L1. So the force of the water is going to be the pressure at the center of area, submerged area, times the area submerged. So again, you have air pressure up here. And the only thing we're acting on for the water pressure, the gate is 8 feet high, but it's only submerged to 4 feet. So our submerged area is 4 feet by 6 feet. And the center of area would be 3 feet down from the top of that submerged area. So in this case, the force is equal to gamma y bar sine theta A. The area is again the 6 foot by 4 foot. The sine theta is given in the problem as 60 degrees, and y bar is 3 feet. It's half of the 6 foot distance, the submerged area. And then lastly, if you look at this thing, here's A, and the force is acting at YCP, and this is the part that's submerged, 6 feet. So L1 is simply equal to that distance, 6 feet, minus YCP. Okay. Now, you can certainly use the equation for YCP, and I will show you that. But when you start at a free surface and go down into the fluid, you have a triangular pressure distribution that starts at 0 and goes to gamma h at the bottom. Where is the center of area of a triangle?
1/3 from the.
Third up from the base. So YCP should be 4 feet. And therefore, L1 would be 2 feet. So if you don't believe me, YCP is equal to the moment of inertia about the centroid over y bar A plus y bar. Moment of inertia about the centroid is 1/12 BH cubed. Y bar is 1/2 of the height, which is 6 feet. And the area is 6 feet by 4 feet. If you calculate that, what you'll get is y bar over 3. And when you add that to y bar, you get 2/3 y bar. Sorry. Yeah. Y bar 3 plus y bar, 2/3. So this turns out to be, either way you do it, by observation or calculation, you'll get L1 is equal to 2 feet. And now you have all the pieces to just rearrange this equation and solve for the tension. And again, I know that was the hardest problem. So the next one, on problem 6, really this is another shear problem. You're given this block sliding down a plane. So we have the weight acting vertically, and the weight acting down the plane is simply the sine of the inclination angle. So in the previous problem, problem 2, you were given the force and you were given all the components and you were told to calculate the force. In this one, you're given the force and you're asked to calculate the terminal velocity. So this is moving at some velocity v. So again, if you looked at the free body diagram of this block, you have W sine theta acting down the plane, and you have the shear force, which is the shear stress, times the shear area, the bottom area of the block. And so this is found the same way. In this case, you had to look up this in the back of your book. And so that is 0.1 Newton second per meter squared. You're given the bottom area of the block. And so again, what you would say from the free body diagram is that W sine theta is equal to tau times the shear area, which is equal to mu dv dy times the shear area. And in this case, we're solving for the velocity. And that's the velocity of the bottom is 0. And we're after this velocity, which is the velocity at the top. Question?
We had a question about the previous problem.
Yes.
Will force on a submerged plane be on exam 2?
Will the forces on a submerged plane be on exam 2? Kind of. Not this way, but in momentum, we're going to need to calculate forces, and that's what I'm going to next. So the answer now is kind of, And when we go through momentum, you'll see what I mean by that. Okay. So for the last problem, that's what you may need to calculate in the future. And you may need to remember that in the future. We're doing lab 6 now. Are they doing lab 6 now or lab 5?
Lab 5.
Is that the sluice gate?
Lab 5 is.
I'm seeing a yes. Excellent. So you're doing this thing right now and you measure the pressure distribution on the back side of this. And we're integrating that into some force of the gate on the fluid. I'm going to be talking about this once I switch over to momentum. Okay. But this is one of those examples where you would need to calculate the force on the submerged object. Okay. Problem 7, again, a gauge pressure is equal to an absolute pressure minus the atmospheric. And in case you didn't know what the atmospheric pressure was in the early problem, here I am giving it to you. Okay? Don't ever accuse me of being a nice guy though. And the last problem, you're given a manometer and then on the next page. And all we're asking is what's the deflection? So in this case, this is the deflection we're after. And again, what we're looking at is the fact that you have a closed space. So all the air pressure up there is under 30 kilopascal. And again, what we can do is start on either side. We can start here at 1, or we can start here at 2. And you work your way from one side of the problem to the other. And when you do that, y should somewhere be in that analysis. So for example, starting at 2. P2, and if we work this in gauge pressure, that's atmospheric pressure, 0. And then what we're going to do is go down through the mercury. I want to get all the way over to here. Well, all we have to do is go down to, say, point A, horizontally across from where the mercury water interface is. Since we're going in a vertical direction downwards, that's increasing pressures, and it's increased the pressure by the specific weight of mercury times y. That gets us to point A on both sides of that manometer. Y is known as the manometer deflection. And now we want to get up to here. Why? Because we have no information there. If we just stop there, we would say that's the pressure at A. We don't know the pressure at A and we don't know why. We need to go all the way to the other side to pull in that information, pressure there. So now we're at this location and we have 2 different fluids. So I'm going to go from A to B, which is at the water oil interface. And we're going upwards now. So that's the negative pressure direction, specific weight of water, times from 1 meter to 2 meters, that's 3 meters. That distance. And then from that point, we're going, that's the same pressure in at the water oil interface at the water and the oil. Then we go from 2 meters to 5 meters elevation, a distance of 3 meters through oil. And again, since we're going upwards, we're decreasing pressure, and that's equal to the 30 kilopascal. So all we don't know in that equation is y. Solve for y. Any lingering questions on just how to set things up? And again, feel free to contact me. By Thanksgiving, it's almost too late to do anything about your grade. If this isn't a wake-up call for you now, then you're not going to get another wake-up call. If you think you're doing poorly, I can't really tell you what your grade is right now. It's relative to everybody else. All I can do is compare it to averages. In the very first slideshow I gave you in this course, first day of lecture, I showed you how to calculate your average. How to put together the homework weights, the lab weights, and the exam weights. You should be able to calculate your average. If you're really having difficulty, give me a call. Okay, so we're going to close down this one. And we're going to open up momentum. So don't feel the need to draw any of these. I want you to think about what you're looking at in the next 5 or 6 slides. Because in each case, I want you to think about what is the fluid. This is a course on fluid mechanics. In each of these cases, there are solids. We only care about the fluid. And in each case for the fluid, what is similar or common between each of the very different cases I'll show. So here's a snowplow. What's the fluid? The fluid, in this case, is the snow. It's sitting on the road, and then it's shooting up off the plow and going in a different direction. Here is, for example, a pipe bend. There's one here, there's one there, there's one there, there's one there, there's one there. They're all over the place. What's happening? Think of what the fluid's doing. Strip away the pipe. Just look at the fluid. Here's a culvert under a road. So this would be a cross section, a schematic of what they look like. So you could have water ponded up upstream and water flowing down here. And here's an example on the left-hand side of what they would look like. Think of just the fluid. Take away all of the solid. Just look at the fluid. And what is similar between the other things we looked at? Rocket thruster. So you may have solid fuel inside, but again, look at just the fluid, that jet at the end. And here's a water cannon. Again, maybe you were at a Justin Bieber concert and you were trying to rush the stage. What always gets me when you have crowd control things like this, one, someone is designing these things to have a purpose. And two, someone is selling these things. And honestly, I don't know how you market these things. Oh, this can knock down 20 people per hour. I don't know. But there's some line that I don't think I could cross that many people do when they're doing things like that. So again, the last one I'll show you is the sluice gate, what you're doing for your lab. So on the right, you see an actual example of a sluice gate. On the left, this cross section that you're looking at in class. Again, think of just the fluid. In all of these cases, what are the commonalities? I'm going to go forward, then I'll go back to a few of them. 1, there is a dramatic change in the velocity vector. Notice this little line over the top. So let's say you had the pipe bend, constant diameter, constant discharge, steady state. What is the average velocity entering compared to the average velocity leaving? You have a constant diameter pipe. What can you say about the two velocities? Numerically, the magnitude is the same. What has changed is the direction, right? And that's what we're going to keep coming to on that pipe bend. Here you have the fluid. Let's go back up to it. What the heck? So here's a pipe bend. Think of this guy right here. And we're going to look down on it. So the fluid goes like this. Coming in, going out. Now, take away the pipe. Mentally take away the pipe. The fluid's moving. Would it just all of a sudden, without the pipe, change direction? Of course not. Next time you're shooting your garden hose in the air, if it just magically takes a 90-degree bend, bring that to me. Okay. So we need that pipe bend to make the velocity vector change. It's not changing the magnitude, just the direction. But that's what the solid surfaces are doing in all of these cases. They're changing the velocity vector. The snowplow, snow's just lying on the road, minding its own business. All of a sudden it's thrown up in the air and off the blade. The other thing that's very distinguishable about all of these cases is that the fluid geometry changes in a very short distance. In the pipe bend, it just takes a turn. let's go to one of the others. Here we go, in the sluice gate. Here you have this cross-sectional flow that is a certain depth at a certain velocity, and after the sluice gate, it's very, very different. So think of the geometry here. Taking away all the externalities, just looking at the fluid. No externalities, just fluid. The geometry of the flow field has changed dramatically in a short distance. That's a commonality. And then the last one is that the pressure distribution varies significantly over the fluid, and typically it's varying non-linearly. So if we go back to that last example, so this is the sluice gate again, without any solid surfaces. What's the pressure at the very top there? Atmospheric? Absolutely. That's not varying, and it's not varying linearly. Similarly, after the sluice gate, we also have atmospheric pressure. How about on the left-hand side? We have atmospheric pressure there. What does the pressure distribution look like in an open channel system? We talked about this the last energy lecture. It's a hydrostatic pressure distribution. Starts at atmospheric pressure at the surface, and it increases as gamma H. We go down. Okay. How about on this side? Same thing. So we have a pressure distribution on each end that starts at atmospheric and goes to whatever the specific weight times the depth is. How about on the bottom? Is there pressure on the bottom? If I put a tank of water on top of you, would you feel anything? Of course there is. And the pressure at the bottom, remember, pressure is a scalar. It's the same in all directions. So this pressure at the bottom of the channel acting this way is the same pressure acting right at that same point. And basically, you have a pressure distribution that's going to reflect the depth of flow. Okay. Have we described the pressure distribution everywhere? Did we miss any place? Sluice gate, right? And that's what your lab is on. So the sluice gate again is right here. Is there pressure up against that sluice gate? Well, we show you the data. We show you with manometers, yes, there's pressure there. And the pressure distribution looks something like this. It starts at atmospheric, and it's kind of hydrostatic. It's linearly changing with depth, but then it comes around because at the bottom of the sluice gate, it's got to be atmospheric again. Is that a linear pressure distribution? No. If we didn't have gauges there, the manometers, would we know what it is? No. So, simple question. Could we convert this pressure distribution on the left-hand side to a force? The end of the channel is the width times the depth. It's a rectangle. Do we know how to calculate forces on plane submerged surfaces? Which is the question we just had. Yes. So if you knew the depth of flow, could you calculate this force and know where it acted? Of course you could. Similarly on this side. This force is the force of the sluice gate on the fluid. And if we knew that pressure distribution, we could integrate it and get it. But typically we don't have those measurements. That's where momentum comes in. We can find the force of the gate in this system by doing a momentum analysis. And we'll explain why it has to be momentum a little bit. The most important thing for momentum is you have a litmus test question that you must always ask when you're looking at problems. And it's a very simple question. Is there a dramatic change in the velocity vector in short distance? If that is true, and that's magnitude or direction, if that is true, then momentum is a player. It doesn't necessarily mean you have to do a momentum analysis, but momentum is definitely there. Typically, why we do a momentum analysis is to find that force, that external force. Why? Because the fluid is generating an equal and opposite force to counteract it. That's the force that we design against. If you have that pipe bend that I was showing before, somehow that has to be braced so it doesn't move. If you have the sluice gate, somehow we have to hold that sluice gate in place. If you have a hydropower penstock that comes down the mountain and then goes horizontally, that force is distributed to the soil. You need to design the foundation to support that system. So typically that's why we're doing momentum problems for the force. Esoterically and academically, you can certainly create a momentum problem where you're trying to find discharges, pressures, or velocities. And we'll talk about those, but they're all solved the same way. So those are the commonalities. So this is the non-calculus derivation of the momentum equation. You can certainly go to your book and look at their derivation. You can do this with the Reynolds transport theorem, and you can read through it and not know water is wet. So I'm just giving you a very simple derivation, quote unquote, and I'm going to make an analogy to continuity, which I don't think anybody had a problem with, because our physical example of how to use continuity was a bathtub. If you can understand how a bathtub works, momentum is philosophically the same thing. So what we say is that we're going to start, whether at the differential scale or when we look at these large chunks of fluid, that Newton's second law applies. Sum of forces is mass times acceleration. And if we're talking about that volume of behind the sluice gate, it's just the volume of the fluid, and it's got some mass times acceleration. And we can expand the mass times acceleration term to be the time rate of change of linear momentum. That's exactly what we did for energy. So in an applied sense, the sharp changes in the velocity vector require that there must be some equilibrating force to create that condition. That is, if we didn't put the sluice gate there, the fluid wouldn't change that geometry so dramatically. If we didn't put the pipe bend there, the fluid would just keep going on its straight path. So again, if you think of going from here to here down to the last one, again, without the pipe bend, the fluid is not going to change course. The force the pipe bend is putting on the fluid is equal and opposite to the force the fluid is putting on the pipe bend. That force of the pipe bend on the fluid is distributed over the surface of the pipe bend. And it's a nonlinear pressure distribution. That's why we don't really go in and measure or calculate what the pressure distribution is. We just calculate that force. That's what we use to design systems. So here's a pipe bend, right? And basically you have fluid coming in here. Sorry, it's going the other way. This is the service in the street. So there's the main street supply. And then you bring that into your house somehow. And you can see a pipe bend here and a pipe bend here. To get the fluid to make this 90-degree bend here or here, we have to apply a force to the fluid. The pipe bend is doing that. And the fluid is creating an equal and opposite force. And that's the force that we have to distribute either to the pipe or to the soil. So again, you would have these pipe restraints, which would keep the pipe from moving, or you would put something on the outside of the bend. They're called thrust blocks. And I realize not all of you take soils. Civils do, the environmentals don't. But basically, I think you understand that if I put on high heels and walked in the sand, I would sink right down. But if I put on snowshoes and walked on the sand, I wouldn't sink down as much. Why? You're distributing your weight, force, over a larger area. And so force, or weight in this case over area, is a shear stress. And what you want that to be less than the failure, or what's known as the allowable shear stress of the soil. So basically, you do the momentum analysis to find this force. And then what you do is your soils analysis to figure out your soil's characteristics. And from that, you can figure out the size of the thrust block area. If this pipe isn't in the ground and it's up in the air, just like these light fixtures in this room, you would need supports. So I don't know if you can see it in any of the videos of the lab, but you'll see that there's an exposed piping system and there are restraints along all the walls holding it in place. I'm sure you've seen cans of soda, maybe even beer. And you take that pop top and you keep moving it back and forth, back and forth, back and forth. What finally happens after a while? Breaks off. That's known as stress relaxation. Every time you're bending this, you're creating a little failure zone in that aluminum cap. Same thing happens in these pipes. If pipes are moving around, sooner or later you get a stress relaxation failure and the pipe breaks. Now and then on the news, you'll see a rocket of water shooting somewhere or a huge cavity under the ground because of pipe breaks. They're incredibly common. And that's just one way they can happen. So we need to restrain these systems. And again, momentum analysis is where it starts. So of course, we're going to talk about a control volume, but what we do is we perform the momentum analysis on a control volume. Think of the sluice gate again. Our control volume is just the fluid. And I'm going to talk about, we won't get to it today, we'll talk about how you draw that. And then what we do is apply the momentum analysis to the control volume. So again, looking at Newton's second law, we say that the sum of the forces is mass times acceleration, which is the time rate of change of linear momentum. And this is the time rate of change of linear momentum of the control volume. If you think of what we did with continuity, for a bathtub, for example, here's your bathtub. We could have the inflow, and if you left the drain open, you'd have the outflow. And depending on the magnitude of the inflow and the outflow, you would either be increasing the volume in the system or decreasing, right? So these are externalities. If we drew a control volume, let's say the inside of the bathtub was your control volume. The fluxes are crossing the control volume boundary. And the right-hand side is what's happening in the CV. That's continuity. What crosses, the sum of what crosses the control volume boundaries is what happens inside the control volume. And we're going to say the same thing for momentum. We can say that this time rate of change of linear momentum of the control volume itself is equal to the sum of, or the net change in linear momentum of fluxes crossing the control volume boundary. Again, think of the sluice gate. We had flux over here, and we had flux over here. If it's steady state, it's the same flow, but because the cross-sectional area is different, we have a change in the velocity vector. So I went a little bit over. This is where we're going to pick up next time, and we're going to do some examples. Momentum is probably the toughest of the three laws of fluid mechanics, so we'll spend some time on it.